In this video, I'm going to talk to you about the combined gas law and Avogadros law. Let's first look at the combined gas law. Now, in the previous video, we discussed three simple gas laws. We discussed Boyle's law, Charles' law, and Gay-Lussac's law. And all three of those laws looked at the interrelatedness between pressure, volume, and temperature. We looked at all three of these conceptually, mathematically, and graphically. So let's revisit this graph of volume as a function of temperature. Notice that the slope of this line is positive and constant. So if I were to find the slope here and the slope here, I would find that M1 equals M2. In other words, if you look at the slope, okay, rise over run, change in y, change in x, we have volume in the y and temperature on the x. That is why this is equal to slope, okay? Now, the reason why I'm going over this is because I want you to understand the mathematical reasoning behind these relationships. So, the quotient of volume divided by temperature will equal a constant K. And so, in order to satisfy that relationship, in this case, which is directly proportional, as volume goes up, temperature must also go up because K remains constant. Let's look at putting these into the combined gas law. So here are the three simple laws we discussed in the last video. We can look at the relationships between all three of them. Now, in Boyle's, we knew that the pressure was inversely proportional to the volume. Whereas in Charles and Gay-Lussac's, we had temperature being directly proportional to volume for Charles and pressure for Gay-Lussac's. So because these all satisfy the same concept of when we look at the slope is constant. Now recall for Boyle's law, we had an inversely proportional relationship, which gave us a hyperbola, but in order to linearize that graph, we were able to graph the volume as a function of the inverse of pressure, which gave us a slope of a positive constant value. Okay, so we can state that the pressure multiplied by the volume, that quantity divided by the temperature, is equal to K. So we're putting all three of these together into the combined gas law. Let's go ahead and define this. This law expresses the relationship between our three variables we've looked at, pressure, volume, and temperature, of a fixed underlined amount of gas. In other words, we're considering the number of moles of gaseous particles to be constant. Mathematically, the combined gas law can be stated as the initial pressure and volume divided by the initial temperature is equal to the final pressure, final volume, divided by the final temperature after some change. Again, this is for a fixed amount of gas. So consider, say, a weather balloon rising into the atmosphere. Well, as it is rising into the atmosphere, the temperature is going down. The pressure is going down. So how would that affect the initial volume? Those are the types of questions we can answer with the combined gas law. Now, let's do one practice problem. If a 2 liters of gas at 35 degrees Celsius and 0.833 atmospheres of pressure is brought to standard temperature and pressure which we've defined and used throughout this course thus far. What is the new volume of the gas? Well, just like we've been practicing, we're going to lay out all the variables involved, and we're going to put what we know, and we're going to put what we're trying to find. Now, on the bottom here, just as a reminder, are all the different units that pressure can be expressed in. So, what do we know? Here's our variables. Here's what we know, and we're trying to find the volume after the change, so the final volume. Recall, when we're dealing with gases, we use Kelvin for temperature, which is an absolute scale. So that is why you see 273 Kelvin plus 35 degrees Celsius, because that's being converted into Kelvin. And as you all know, at STP, our temperature is 0 degrees Celsius, and our standard pressure is 1 atmosphere. So by looking at these variables and utilizing the combined gas law equation, we're able to solve for the new volume. So let's go ahead and make a prediction here. So we have a gas initially at 308 Kelvin, but it is brought to standard temperature, which is at 273 Kelvin. So the temperature has gone down. Well, when the temperature goes down, the volume goes down. All right? Those are directly proportional. Let's look at what else happens here. We have an initial pressure of 0.833 atmospheres. It is brought to 1 atmosphere. So pressure is going to go up. Pressure is going up. Temperature is going down. Well, remember, according to Boyle's law, which states pressure and volume are inversely proportional to one another. So if pressure is going up, volume is going down. So in both instances here, we would predict that volume will go down or decrease. Let's go ahead and put in some numbers here. We're going to rearrange this algebraically to solve for volume 2, which is the new volume of the gas. So by multiplying both sides by 273 Kelvin, dividing both sides by 1 atmosphere, we find our final volume to be 1.5 liters, which is indeed less than 2.0 liters. All right. There he is. Amadeo. Lorenzo Amadeo Carlo Avogadro. All right, so Avogadros Law. We visited this earlier in the course when we talked about molar volume, which was expressed as liters in a mole. All right, so we've already looked at this and we briefly touched on it when I explained the conditions for STP in earlier units. So Avogadro's law, the volume of gas is directly proportional to the amount of gas at a constant temperature and a constant pressure. This is intuitive. This is a directly proportional relationship. As the volume increases, the number of moles are increasing. So think of a balloon. When you blow into a balloon, the volume gets bigger. Well, what's going into the balloon? You're increasing the moles of gaseous particles into the balloon. The balloon gets bigger. So this law is conceptually very intuitive. And it's yet another example of where when we graph volume as a function of the number of moles, we get a slope that is constant and positive. And so what do we know about that from the discussion at the beginning of this video? Well, we know that the slope is constant, so this must be equal to k, which is equal to the slope in unchanging. let's go ahead and look at this mathematically. So as the number of moles increases, the volume increases. And conversely, as the number of moles decreases, the volume would decrease. All right, so here we have a diagram that illustrates this. On the left, we have 1 mole of a gas under 1 atmosphere of pressure, and the volume under these conditions at 273 Kelvin is 22.4 liters. Now we're going to double the amount of gaseous particles, which means we're going to double the volume to 44.8 liters. Again, very intuitive. Let's put this all together. So we have Boyle's, Charles, and Gay-Lussac's law. We've looked at them conceptually, mathematically, and graphically. I've gone through the intuition for the graphical method and the fact that the slope is constant. Therefore, we can say pressure multiplied by volume equals some constant K. Likewise, we can do the same for Charles and Gay-Lussac's. So when we looked at these different laws, we stated volume was proportional to the inverse of temperature. We stated volume was proportional to temperature, and pressure was proportional to temperature. So now with Avogadro's law, we can now finally include the number of moles. All right, so volume is directly proportional to the number of moles. So if we were to take all 3 of these and put them together, we could show that volume is proportional to moles times temperature, that quantity divided by the pressure. All right, so all I've done is I've looked at the commonalities here of all of these relationships, put them into one, and saying that it is proportional to moles times the temperature and that quantity divided by pressure. So let's take it one step further here. Let's say that the volume is now equal to some constant, and that multiplied by the product of moles times temperature divided by pressure. So all I've done here is I've taken into consideration that all 4 of these are equal to a constant. And so if I put that constant in, I can take the proportional symbol out and put equals in along with that constant, and we get this relationship. Let's rearrange this a little bit. Let's multiply both sides by pressure. And what we get is basically the derivation for the ideal gas law, which is going to be the topic of gases video number 5. So I have showed you how to derive the most common, most used gas law that we will be using throughout this course. We've looked at our standards again, dealing with conceptual, quantitative, and graphical representations that are analyzing pressure, volume, temperature, and finally, including the number of moles of a gas. I'll see you guys in class.